Allow me to introduce how to represent certain types of functions as sums of power series by manipulating geometric series or by differentiating or integrating such a series. Scientists do this to simplify the expressions they deal with. Computer scientists do this to represent functions on calculators and computers. Wow, that sounds like a lot of work and a lot of difficult stuff. So let's do the basics. So representation of functions as a power series. So here I have a geometric series, and then on the left hand side I start with 1 divided by 1 minus x, so that is equal to, so 1 divided by 1 minus x is a simple rational function, right? That function is equals to 1 plus x squared plus x to the third, x to the fourth. So as you can see that the power has an increment of 1, so overall that is the summation and go of x raised to the nth power, where n goes from 0 to infinity. So when n is equals to 0, x to the 0 power is 1. When n is equals to 1, x raised to the first power is x, and then n equals to 2, you have x raised to the second power, so on and so forth. So this just look like a geometric series where the base is equals to n, right? Back in the geometric series, we say the geometric series is convergent when the base, which is the common ratio, or in this case, the common ratio is x less than 1. And then why do we have to use less than 1? So why? Why less than 1? How come that is not less than 2, not less than 3, not less than 1,000? So in the previous lesson, the power series, I already discussed this matter. So let's do that again. Why do we have to say the absolute value of x or the absolute value of common ratio is less than 1? So first of all, let's take a look at this inequality with a absolute value. So the absolute value of x is less than 1 is the same thing as x is between -1 and 1, not including 1 and -1. There is a reason. So let's say we pick an x value that satisfy the inequality. So I have 3 tries. The first one is I let x equals to 0. So when x is equals to 0, what happens when n is huge? So we have 0 raised to the infinity power, so that means you have 0 multiplied by itself many times, right? So you get a 0. What happens when when x is a little bit greater than 0? So let's say a 0.5. So if you have a 0.5 power, you can try this on your calculator right now. You take the base 0.5 and then you raise the 0.5 to a very large exponent. So once you press enter, you will see that the result is not equal to 0. You will see a scientific notation with a e and then minus some power on the right hand side. So that is a scientific notation. That means the result is a very small value and it is very close to 0. So if you take a negative, so let's say negative 0.5 or negative 0.6, you raise that to a very large power, you will get the same thing. The result is something that is extremely close to 0. So when that happens, we say that the sum of the geometric series is equals to a real number. So that's simple. The R is real number. So because the sum is determined by the first several terms, you have 1 plus x squared plus x to the third, right? So look at the exponent. When the exponent is so big, that term, the one individual term, is just something so close to 0. But when the exponent is not large, so let's say second power, third power, you get some value. So that means the sum, if you take a look at the expansion of the series, the sum is determined by the first several terms of the geometric series, maybe the second power to the 10th power, or from the second power to the 7th power. So those value determine what the sum is. When the exponent is so big, you will just get a bunch of 0. So adding a bunch of 0, not exactly 0, adding a bunch of numbers so close to 0, that doesn't really affect the sum, right? You only add a tiny little piece to the current sum that doesn't affect anything. So that's why I said the sum is determined by the first couple terms. As a result, the sum is equals to a real number, and therefore the geometric series is convergent. So here I want to test the left hand side of the equation, the pink one, 1 divided by x. So for the 1 divided by x, let's play around that a little bit. So I let x equals to 0.5 because I just said that when x is between -1 and 1, we have a convergent geometric series, right? So what happens when x is equals to 0.5? Let's just plug in the 0.5. On the left hand side, the pink the pink side, you have 1 divided by 1 minus 0.5, and then on the right hand side, you have 1 plus 0.5, 0.5 to the second power, 0.5 to the third power, 0.5 to the fourth power, and then so on and so forth. So let's dig a little bit deeper on the left hand side. So 1 minus 0.5 is equals to 0.5, right? And then 0.5 is just a 1/2. 1 divided by a 1/2 is equals to 2. So you don't need to touch your calculator. You know, on the left hand side, we have equals to 2. What happened on the right hand side? So on the right hand side, you have 1 plus 0.5, right? So those I already handle the power for you. So when the power is equals to the first you have a 0.5. When the power is equals to 2, you have a 0.5. So as you can see, when we raise the power, so from n equals to 2 to n equals to 7, just compare n equals to 2 and n equals to 7 this time. When n equals to 2, we have that, but if you raise the n to a 7th power, do you see that how small the result is compared to n is equals to 2? So that's why I said when you add this number up, the sum is really determined by the first several terms. When n is so large, so let's say when n is equals to 100 power, 0.5 raised to 100 power, you only get a number that is so close to 0, which doesn't affect the sum at all. So if you just add from n equals to 0 to n equals to 7, I did the math for you. So on the right hand side of the equation, you have 1.9921875. So we can say that is close to 2. It can be getting more closer and closer to 2. All you have to do is you take a look at you add more terms to it. So let's say n equals to 8, n equals to 9, n equals to 10. The more terms you add to this sum, the closer the sum will be closer to 2. So the sum is approximately equal to 2, and it is determined by the first several terms. So when n is large, so let's say n equals to 20, this one I also did the math for you. So 0.5 raised to 20, you get a 9.54 times 10 to the negative 7. So on your calculator, you should see 9.54 and then a bunch of number, and then on the right hand side, you see a base, you see a uppercase E, and then minus 7. The base E is the E is a base 10, and then the minus 7, the minus 0.7, whatever that is the exponent of 10. So this is called scientific notation. You are taking a calculus class, I expect you to know what scientific notation is. That is one of the ways to write a very long number in a very compact form. So if you put this back to a decimal, so that is 0 point followed by 60954, which is very close to 0, right? When you add numbers like that to the sum, that doesn't affect the sum too much. So you still get 1.99 something, right? Okay, so moving on to the geometric series. So this is not a new lesson. So geometric series is what we learned in the past, and we will have to employ these things again. So that's why it is good to recall what it is, to take a look at what it is again. So for the geometric series in this section and the previous previous lesson, the power series, instead of using R, we have x raised to the nth power, and then I want to recall the geometric series. So the geometric series, it can start at 1, it can start at 0, so depending on which textbook you use. So the geometric series is the summation, n goes from 1 to infinity, and then on the body of the series, we have a constant times r, which is the common ratio, raised to n minus 1 power. So when n equals to 1, we have the power is n minus 1. When n starts at 0, the power is just equals to n. So on the right hand side, the expansion, you get the same thing, right? So you get a plus ar to the first, ar squared, ar to the third, ar to the fourth, so on and so forth. And this is called a geometric series. The geometric series is convergent if the common ratio, absolute value of r, is less than 1. That leads me to r is between -1 and 1. So since the geometric series is convergent in this case, we are able to find the sum. The sum is equals to a real number. So the sum is the first term divided by 1 minus r. And then r again is a common ratio. I already mentioned this many times. And what about divergence? So when r is the absolute value of r is greater than or equal to 1, the sum is equals to infinity, the sum is big, so the series is divergent. And then we draw a picture to summarize the two cases. So just like how we discussed the interval of convergence, we draw a line, and this line represents x. So between -1 and 1, the series is convergent, right? And then if the common ratio is outside of this interval, so let's say less than -1, I forgot a negative right here, less than -1 or xr is greater than 1, then the geometric series is diverged. All right. So so overall, how do we explain the big picture using my own language? So using my own language, so let's say when you do algebra, you have function like this, right? So 1 divided by 1 minus x, and then you call this f of x, right? So let's say when x is equals to 0.5, you have f of 0.5 that is equals to 1 divided by 1 minus 0.5, and then you tell your instructor what that equals to. So this is called function evaluation. Is what you learned back in algebra and pre-calculus, but in this section, representation of function as a power series, we are going to something that is a little bit fancier than that. So the idea is, so if you let x equals to a certain number, so let's say x is equals to 0.9, and then you will get a function evaluation using the language or the knowledge back in pre-calculus or algebra, right? But using the stuff you learn in calculus, so what happened is, so once you take 1 divided by 1 minus 0.9, what the calculator or the computer does is they plug in a 0.9 to every x value on the right hand side, which is the expansion of the power series, and that is how they give you approximation. So just like stage 1 and stage 2. Stage 1, you take intermediate algebra, you take pre-calculus, you learn function evaluation, fine, good job. But in calculus, we are going to take one more step forward. We are going to look at the power series. So to explain how you get approximation, you have to get the expansion of the power series. So when you plug in a number to the function, that is the same thing as plugging in the same number to a power series. All right, so that is how to explain this using my own language. If you think my instruction is helpful, which is, all right, let me know in the comment section below. Please help me on this. Like the video, subscribe to my channel. It only takes you 10 seconds to do so. I appreciate your help a lot. So watching my channel is way better than reading a book, right? I agree with you. Yes, that is yes. That's why it is worth it to come back to my channel. That's why you have to subscribe to my channel. In the next lesson, I will show you some example using every concept I talk about in this video. All right, I see you all in there. Signing off for now.